Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at another calculation, again from an AQA paper. This time we're going to have a look at a redox titration, only we're not dealing with iron as the species being oxidised. In this particular redox reaction we're using hydrogen peroxide. And I chose this question because the final part where we're thinking about the original concentration of the hydrogen peroxide, which is what we're asked to calculate, can be a little bit tricky because we're starting with a set volume of the hydrogen peroxide rather than a mass like we might do for the iron, and then that volume is made up to the volume in the volumetric flask, and then we're using a proportion of that, and we really need to think about how many moles of hydrogen peroxide are present in each of the different steps. So it's also good to practice the writing of our redox equation, because I'll show you how to do the oxidation equation, the reduction equation, and the overall redox equation, and which things you need to have learned and which things you can work out through application of your skills. And then we'll have a look at the calculation. What I also really like about this is that AQA have given you the ratio in case that's the bit that you get stuck with. So if you can do the calculation but you aren't sure how to do the equations to get the ratio, they've given you a ratio here. It's not the correct ratio, and if you're able to get a ratio, I would suggest using whatever you've got, even if you're not 100% certain that it's correct, because you will get error carried forward marks. But heaven forbid you couldn't do the equations at all, then you can at least get the marks for the calculation, which I think is very fair of AQA to do. So I'm going to use two colours for my hydrogen peroxide and my potassium manganate, and I will do my highlighting and my annotating and my worked answer and come back and go through it all thoroughly with you. Okie dokie, so the question says that hydrogen peroxide is used as an oxidising agent in the preparation of transition metal complexes. The concentration of a hydrogen peroxide solution can be determined by titration with acidified potassium manganate 7 solution. In this reaction, the hydrogen peroxide is oxidised to oxygen gas. 5 cm³ sample of the hydrogen peroxide solution was added to a volumetric flask and made up to 250 cm³ of aqueous solution. A 25 cm³ sample of this diluted solution was acidified and reacted completely with 24.35 cm³ of a 0.0187 mole per decimeter cube potassium manganate 7 solution. Write an equation for the reaction between the acidified potassium manganate 7 solution and hydrogen peroxide. Use this equation and the results given to calculate a value for the concentration in moles per decimeter cubed of the original hydrogen peroxide solution. So, the equation we need to write needs to be a redox reaction, and we are helped out, as we would expect to be, for the hydrogen peroxide equation. We've been told that the H2O2 will be oxidised to oxygen. Those are the two things that I then wrote down, and I then did my arrow in between, and then using my redox writing equation skills from year 12, I went, okay, my oxygens are balanced, hydrogens not so I'm going to add 2 H pluses to the right side. Charges are then not going to be balanced, so I'm going to add 2 electrons onto this right hand side. That then has balanced my atoms and my charges, and my oxidation half equation is done. For the manganate half equation, which is going to be reduced, which again, another clue, hydrogen peroxide is used as an oxidizing agent in the preparation of transition metal complexes, but interestingly it is itself being oxidized here and being used as a reducing agent. So interesting that it's included that in the wording of this question. Moving swiftly on, the manganate ion is definitely being reduced, and I know that because A, it's gaining electrons, and B, the oxidation state of the manganese is changing from +7 down to +2, which is a sign of reduction. The oxygen in the H2O2 is -1. Usually oxygen's -2, in a peroxide is the exception, so it's -1 here and it's 0 here. So we've increased the oxidation state, which is oxidation. Apologies for any confusion caused there. Not quite sure why that sentence is there. Anyways, the bit that we need to know for the reduction half equation is the MnO4- and be able to write the formula for that. So it's potassium manganate. Potassium is K+, so that means the manganate has an overall charge of minus, and manganate, if it ends in 8, it contains oxygen, and the 7, Roman numeral 7 in the brackets, is the oxidation state of the manganese. So you might be able to work that out if you don't know it, but you'll probably get really familiar with that by doing lots of questions. The other thing we need to know is what it's reduced to, which is the Mn2+. So again, as I've spoken about before, I did the MnO4-, left a space, did my arrow, wrote the Mn2+, and then I went about using my half equation skills to go, okay, manganese is balanced, oxygens are not, I'm going to add 4 waters onto the right therefore. Now my hydrogens are not balanced, going to therefore add 8 H pluses to the left side, and then to make the charges be the same, the current charge was 2 plus on the right and the minus and the 8 plus, so 7 plus on the left. Adding 5 electrons to the left would then mean the charges as well as all the atoms were balanced. Now when we combine half equations, again as I've spoken about before, we have to have the same number of electrons on both sides. So we're going to have to, in this instance, multiply up both equations. We're going to need to times the top one by 5, so that we've got 10 electrons, and we're going to need to times the bottom one by 2, so we have 10 electrons. Now I have written both of those out separately again, and some people won't do that. Some people will just combine them and multiply all at the same time. I think that is kind of tempting fate a little bit in terms of making a mistake, but I understand that obviously from a time save point of view, rewriting both the equations out again isn't the most time effective way of doing things. So whatever way you choose to do it, please just take care. One of the things that also happens is we can see, we've got 10 H pluses on the right and 16 of them on the left. So when you then combine your two equations together, you can cancel out all the H pluses that will appear on the right and bring down the number of H plus ions on the left from 16 down to 6, because 10 of them got used up. So then 6 are remaining. And then as with any redox equation, we are combining everything that appears on the left hand side of both of the half equations. So the 5H2O, the 2MnO4-, the reduced number for the 6H plus, not going to add the electrons because they're going to cancel, then our arrow, and then everything that appears on the right hand side of both equations. So the oxygen, no H pluses because they've cancelled, no electrons because they've cancelled, the 2 Mn2+, and the 8H2O. Now we have to do that, and you can't go straight to writing a redox equation. You have to do the half equations first, which I know is laborious, but there is no way for you to get the reacting mole ratios for the hydrogen peroxide and the potassium manganate without doing it this way. So that's how it is, I'm afraid. Now we've got that ratio of 2 moles of the manganate to 5 moles of the hydrogen peroxide, and we were given in the question the volume and the concentration of the potassium manganate solution. So I've used those concentration and volumes and times them together to get the number of moles of the potassium manganate as 4.55 times 10 to the minus 4 moles. Using the 2 to 5 ratio, again, I could have just times by 2.5 for those of you that are more mathematically inclined. I like to divide by 2 and then times by 5, so work out what 1 part would be and then work out what 5 parts would be. And that gave me a value for the moles of 1.14 times 10 to the minus 3, and that was in 25 centimetres cubed, because it said that a 25 centimetre cube sample was then reacted with that amount of the potassium manganate. So as we've done in previous questions, if we know the moles of the H2O2 in the 25 centimetres cubed, we can figure out how many moles there had to have been in the 250 centimetres cubed, because we've then taken a tenth of that overall solution and done a reaction with it. So in the original 250, we're going to have 10 times the amount of moles, which comes out as 0.0144. Now this is the part that I think is a little bit tricky to get your head around potentially. We start with a 5 centimetre cube sample of hydrogen peroxide. That was added to the volumetric flask and made up to the 250, and then we're taking a tenth of that. Some students here might be tempted to divide the number of moles in the 250 down to work out how many moles are in the 5, but the moles is the same. If I have 5 centimetres cubed and I stick that into my volumetric flask and I then add water to that, I'm not changing how many moles of the hydrogen peroxide were in that 5 centimetre cubed by adding water, so the number of moles will be the same. Some students would then ask me, well, why, when we only then take 10 or a tenth out, so take out the 25 centimeters cubed, why does the moles not stay the same? Well, at that point you would have a solution that was homogeneous, the concentration of it would be the same throughout, and the moles would be dispersed throughout that volume. So if you then take a tenth of it, you can't possibly be taking the same number of moles unless all the moles happen to be sat in that 25 centimeter cubed portion, which you avoid doing by inverting the flask several times. That's the difference. But when we initially dilute it, we're going, right, there's 5 centimeters cubed of the bleach that's got the moles. It's not bleach necessarily here, it's hydrogen peroxide, my apologies. We have got the 5 centimeters cubed of the hydrogen peroxide. We're then just going to add water to that. That isn't changing how many moles we've got. We're just diluting the concentration, but the mole stays the same. So if we then want to know the concentration of the original hydrogen peroxide solution, we've got the moles, and in the beginning, that amount of moles was only in 5 centimeters cubed. So we can get concentration by doing moles divided by volume, and I get an answer to 3 significant figures of 2.28 moles per decimeter cubed. That's one of the reasons why we probably dilute it, because that's very strong. So by diluting it, we're keeping the same number of moles, but if that's then in 250 centimeters cubed, we can see that obviously the concentration is going to decrease a lot because the number on the bottom of the fraction would be much bigger. And that's getting your head around dilution and how the number of moles isn't changed or isn't affected when we add water to make up the original 5 up to 250 centimeters cubed. If I've not explained that clearly enough, please do let me know, or if there's any other questions about this or similar redox titration questions that you might have come across, please do send them my way. Always very happy to receive and answer questions. Thank you so much for watching, everyone. I hope you have a really great day.